A flexible fuel system is one that's fitted to a vehicle, enabling it to operate on regular unleaded or a blend of regular unleaded and up to 85% ethanol fuel. Flex fuel vehicles experience no loss of power and torque when using an E85 blend. In fact, it's possible to increase both of these outcomes with a pure E85 tune. To understand how this is possible, we need to understand all the requirements of an engine when operating on this fuel. A flex fuel, or fuel composition sensor, is a device that measures the ethanol content in the car's fuel system. The sensor is most often located between the fuel tank and injector rail, but some aftermarket performance manufacturers choose to install it in the return line so as not to restrict the fuel delivery to the engine. The sensor is basically a cylindrical capacitor consisting of two tubes, which make up the inner and outer electrode. A high reference or ignition voltage and a low reference or ground is supplied to the sensor by the engine's ECM. This voltage is modified and conditioned by the internal electronics and applied to each electrode of the sensing tube. The signal output is then returned to the ECM. The capacitance value of a dry sensor is converted to a PWM signal with a fixed frequency. This signal is calibrated to the ECM. When unleaded fuel is pushed through the sensor, its capacitance value will change. This is because unleaded fuel has a different permittivity to air. The new capacitance value is converted by the sensor to a PWM with a different frequency to when there was no fuel in the system. Ethanol has a different permittivity again when compared with unleaded fuel, so any blend from E10 to E85 will have a direct effect on the sensor's capacitance, and therefore the frequency of the PWM output. The higher the ethanol content, the higher the sensor capacitance. Some flex fuel sensors are also designed with a fuel temperature sensor mounted close to the sampling tube. Temperature information can be signalled to the ECM on the same circuit. This is achieved by altering the signal pulse width only. We see this same technology used in 8-wire air mass sensors. The ECM takes both frequency and pulse width signals and converts them to usable alcohol content and fuel temperature values. The ECM can then decide the best injection pulse width and ignition timing for the fuel entering the engine. Ethanol has a much lower energy density level than unleaded fuel. This simply means that to produce the same power and torque, more ethanol is consumed. We all know that the stoichiometric air-fuel mixture for unleaded fuel is 14.7 parts air to 1 part fuel by mass. But did you know that E85, due to its lower energy density, sits at around 8.7 parts air to 1 part fuel at its stoichiometric ratio? So for any standard flex fuel engine operating on E85, about 30% more fuel by volume must be delivered to the injectors for combustion. This way, the same torque values are achieved as if the engine were using regular unleaded fuel. When the driver fills the fuel tank with regular unleaded, the flex fuel sensor reports a 0 alcohol content to the ECM. The ECM then reverts to its unleaded map and the driver does not notice a change in performance. Production flex fuel engines are designed with compromise in mind. The compression ratio, and in the case of a turbocharged vehicle, boost pressures, must be low enough so that detonation will not occur when the system is operating on regular unleaded fuel. Variables such as injector pulse width, ignition timing, and to some degree, cam phasing can be altered electronically by the ECM, making the transition between different fuels possible. In a spark ignition, internal combustion engine, the purpose of advancing the timing or triggering the spark earlier in the crankshaft cycle is to get past the ignition delay. Ignition delay is the time that it takes to fully ignite the air-fuel mixture within the combustion chamber. more energy is wasted in this process than any other. So the goal of an engine design is to maximise all available energy from the fuel-air charge. The idea is to ignite the fuel-air charge in the combustion chamber with enough lead time to create the highest cylinder pressure for the engine design. And this is where a lot of horsepower is found. More timing advance and higher compression pressures. The theoretical point for the highest cylinder pressure occurs around 20 degrees after top dead centre on the power stroke, which maximises leverage on the crankshaft. Due to rotational speed changes of the engine crankshaft, initialisation of spark may occur very early in the compression stroke to meet these design needs. E85 burns richer than unleaded, so when ignited it has a much slower flame front, so the ignition timing must be more advanced again than what is acceptable with regular unleaded fuel. The flame front may be slower, but ethanol fuel is more volatile, which can result in uncontrolled detonation across the charge once ignited. For this reason, special additives are blended during the processing stage of E85, which increases the octane rating to around 105 RON. This is quite substantial when compared with unleaded 91 or even premium 98. The real benefit of E85 as a performance fuel is that with such a high octane rating, detonation can be effectively controlled. This allows for greater engine compression ratios and higher boost pressures to be used. Again, the higher the compression ratio, the greater the pressure achieved during combustion, resulting in more torque at the crankshaft. Ethanol is an oxygenated biofuel, and as such, when combusted, it releases CO2 and oxygen as tailpipe emissions. This is really good if ethanol was used in its pure form. An E85 blend still produces hydrocarbon and other noxious emissions when burnt in an engine's combustion chamber, although they are far less than a pure unleaded fuel charge. An 85% ethanol blend will not harm or hinder the operation of any exhaust treatment devices, such as catalytic converters, or even the operation of oxygen sensors. But if we look at the amount of CO2 and hydrocarbon emissions produced during the processing of ethanol fuel, the end may not justify the means. On one hand, we have a greener alternative to regular unleaded fuel, which only requires some additional hardware and software to operate in most production vehicles. And on the other, E85 is not as readily available for purchase as regular unleaded, and the vehicle will consume more of it while producing the same power and torque levels. With major mechanical alterations such as increased compression, greater turbo boost, high flow fuel and high voltage ignition systems, this fuel will deliver greater levels of performance and torque. While an E85 fueled performance vehicle may not be for everybody, a flex fuel option on a standard car might be the answer to reduce our reliance on fossil fuels.